Now, as I discussed in the previous session that we have to discuss about the derivation for the magnetic and the electric field components for a half wave dipole. So, today's class what we do is we try to derive these two equations. Remember, in the earlier class we have solved one problem based on the half wave dipole radiation resistance, which we have got as 73 ohms. So, to get that particular 73 ohms we have to start from these two equations. Okay, so now how do we derive these two equations? Let us try to go with the derivation part of this equation. So what is the equation H phi that you have to remember? It is going to be Im by 2 pi r into cos of pi by 2 of cos theta by sin theta ampere per meter square. That is the magnetic field equation along the phi direction. The next one is going to be the electric field equation along the theta direction. Remember, in antennas and wave propagation we are going to consider the spherical coordinate system. The spherical coordinate system points are going to be what now? It's going to be the radius r of the sphere, and next is angle theta and angle phi. So these are the various parameters that we normally going to have. So therefore we will be getting the parameters in terms of h phi and e theta. So next e theta we have substituted as 60 Im by r into cos of pi by 2 cos theta sin theta volt per meters. So these two equations we have directly written in the problem. Okay, to solve the problem for radiation resistance we have substituted these two formulas directly, and we have solved by using the method of integration. We have solved this. Let us, in this today's session we will try to go with the derivative part of these two particular concepts. Okay. Now first of all we have to start with the electrostatics or magnetostatics. So in the earlier classes, that is in EMTL subject, we have studied about the electrostatic basic equation. The electric field is related to the potential V is equal to E is equal to minus del V, where V is known as the electric potential and E is known as the electric field vector. Similarly, we have studied about the magnetostatic fields. So using magnetostatics, the H field, that is a magnetic field vector, is equal to del cross V. And if you normally take this as some vector A, we can take this as some vector A. Now where A is nothing but the magnetic vector potential or magnetic something like vector potential or something like a potential for us, magnetic potential. And the same equation we can approximately write it to B is equal to del cross A. Okay, because B and H are both are directly proportional to each other. So therefore we can write B is equal to approximated to del cross A for us. Now let us start working with the antennas now. While starting with working with antennas, we go with the ideal conditions. What is the ideal condition? Ideal condition is going to be for a homogeneous isometric medium. Means what? It is known as a lossless medium. When you consider a lossless medium, using the Biot-Savart's law, we have developed the differential magnetic vector potential is directly proportional to IdL by R, where I is nothing but the infinitesimal, where DL is nothing but the differential component, and the current flowing through this infinitesimally small component, okay, which is nothing but I into DL. Okay, so that is what that means. This becomes a source of the radiation towards a point P. For example, say for example the antenna is radiating from this point towards the direction called P. So this is what the condition, let us suppose we have. So when we have that condition, using Biot-Savart's law from magnetostatics, we have already defined that the magnetic vector potential is directly proportional to the source and inversely proportional to the radial distance. So therefore the source is nothing but is equal to I into DL, and it is inversely proportional to R. Next, in terms of equation, when we will write this dA is equal to some k times I into dL by R, where I is known as the constant, medium constant. Now here we are talking about magnetostatics, so therefore we normally going to have the permeability equation. So that means we normally going to have the permeability as the medium constant. So this permeability by 4 pi. Why 4 pi? Because we are considering the spherical coordinate system. So we normally going to consider this as mu by 4 pi. So this k is replaced with simply mu by 4 pi. Okay, k is replaced with simply mu by 4 pi. So now the entire potential from this small, infinitesimally small portion towards the direction, towards the point P under consideration, we can get it by applying the integration. So we apply the integration to left hand side, right hand side. So because of this integration and differentiation will get cancelled. We get simply some potential A. So this A is known as magnetic potential. So this potential A is equal to integral of mu by 4 pi. Then next, what I can write this I into dl as? Now in a spherical coordinate system, we will write this as in terms of the volume density. So this will write this as simply volume density, J into dV by R. We will write this in terms of volume density, and we will write this in terms of the volume density of the current. So this is something like density component. J is nothing but density component. So this I into dl will normally going to write it in terms of the magnetic component. So therefore this something like, if A is going to be a constant one, if A is going to be, say A is going to be constant one, what is generally J is equal to? J is equal to I by A. What is J? I by A. J is nothing but the current density. So current density is equal to, general formula is what? I by A. Okay. So if I is going to be fixed, I can write this I into dl is equal to something like J dV in terms of the volume constant. So that means in a spherical coordinate system we normally going to consider the volume. Therefore this part, is I into dl, will replace it with J into dV. So that means here we normally going to consider the volume integral for the spherical coordinate system. So therefore we will consider as volume for a spherical coordinate system, and we can write this equation as mu J dV by 4 pi r. Now here we are dealing with a dipole antenna. Okay, what is dipole antenna? It is going to have two polarities. One is going to be positive. Say imagine this is positive. If it is positive, this will be definitely negative. If this is positive, that will be simply negative for a dipole antenna. Right. Now if you imagine that the dipole antenna length is going to be 2h. Now this side is going to be minus h, this side is going to be plus h. So therefore the resultant length is going to be simply h minus of minus h becomes 2h. Next the radial distance, that means the radial distance from the point z is equal to 0 to the point P of radiation is nothing but equal to, say, capital R. If you take that radial distance is equal to capital R, I can replace this R with, say, capital R in the spherical coordinate system. So now this small r I replace with a capital R in the spherical coordinate system. Now this part, when I am going to expand for a spherical coordinate system, what is that I am going to write it here now? Yeah, this is R I have taken now. Right. Now here this current density part, how is that I am writing this current density part? This current density part I have to consider by considering all the complex components. So whenever you are going to consider the complex components, you have to compulsorily multiply it by the e power minus j part, e power minus j beta. Why j beta is going to come into picture? Because beta is nothing but a propagation constant for us. If propagation constant is normally going to be there, means the wave is propagating in the medium. That is the meaning of a propagation constant. So therefore e power minus j, in which direction it is moving now? Towards our direction that we are representing, it is moving in that. So therefore what we do is here, we simply multiply j written keeping in view of the r, okay, into e power minus j beta r. So this is what you have written here. Now as far as this integration is concerned, this is integrated with respect to volume. So therefore the rest of the part are nothing but constants. I will simply take it outside. So integral of volume j dot dv. Now here this particular situation is going to be simply line integral part. This line integral, we are applying the spherical, we are applying the dipole conditions keeping in view of the line integration. So when you convert this volume to line integral, what we can normally write this as? J is equal to simply I into dl. That means previously whatever that we have represented here. So this J is equal to, we will write simply once again same notation now, I into dl, and I will write this in terms of the line integration. So when you write this in terms of line integration, what is the equation I will get now? Mu e power minus j beta capital R by 4 pi capital R. Okay. So integration of this I into dl along the AZ direction. So that means this particular wave is moving along the Z direction. So we are assuming that the wave is moving along the say Z direction. So under that condition, when you consider the electric current I is normally flowing, which is normally variable in nature, then we can represent the magnetic vector potential. So this is known as a magnetic vector potential. Magnetic vector potential. So this potential equation is equal to something like that we can write. Now after we do this, we should now extend this to a dipole now. Okay, now how do we extend this to a dipole now? Now we will write it for the dipole, antenna now. When you consider it for a dipole antenna, so this component I can write it as a differential component, because you are going to have two sides of a dipole antenna. Okay, dipole antenna is going to have two things. This is one polarity, another polarity, another pole. Two poles you are going to have. So therefore, we consider that as a differential component, whatever that we have got as the magnetic vector potential. So we will consider the differential component A is equal to, now we have got an integration of I into dl. So that means this I is normally going to be a constant, so I will take outside. Then this dl, what about dl now? dl is normally going to get integrated with respect to minus dl by 2 plus dl by 2, where the length of this straight line or length of the line is taken as equal to dl. So therefore obviously we are normally going to get dl, right? Now if you consider along z direction, the dl is represented with z. So therefore I can represent the wave can be propagating along the say z direction. Okay. So this is what the basic equation which we get for the dipole from the previous equation. So after this, if I is going to be asymptotically distributed sinusoidally, so if I is varying asymptotically, means what? What do you mean by asymptotic? There will be some amount of leakage current, okay, nearer to the poles of the dipole. So that is what, it don't become zero totally. So when something don't become zero totally, it is something like called as asymptotic. So here we take a condition, if I is asymptotically distributed sinusoid, then the sinusoidal value should be written in terms of sine component. So therefore I will write this in terms of I is equal to, general formula is what now? Sine function. It is something like Im sine omega t plus theta. General wave equation, this is general time domain wave equation now. So now here also we will write it here, but here it is going to be in terms of wave in the z direction that we are writing, keeping in view of the height of the antenna. So therefore we will write this as Im sine, we are writing in terms for the wave. So since we are writing it for wave, we will introduce this term called beta. Beta is known as propagation constant. So we have to write in terms of propagation constant. So beta into h minus z, where h is known as the height of the antenna and z is normally going to be the propagation. That means if we consider the z, that means if the propagation is something like this, so that means here this is, say, this point we have taken z is equal to 0. Okay. So if this is for z greater than 0, that means here this particular wave is taken as equal to, as we are coming towards 0, it is not just below 0. So we will take this as z greater than 0, and therefore we are moving in a positive z direction. So as we are moving in a positive z direction, we will take minus z, h minus z. Similarly, when you move towards negative z direction, we will do opposite, h plus z will write. So sine beta of h plus z will write. Okay, please remember these two equations. Okay, so once again deriving these two equations takes around 1 page for us. So therefore I am skipping the derivative part. I am just simply making you to write directly from the basic wave equation. Okay, so since we are considering them as distributed sinusoidally, which is asymptotic in nature, if it is asymptotic in nature, there should be similar kind of a distribution towards the positive z as well as negative z direction with respect to the height of the antenna, and the wave should keep propagated. So if the wave is propagating, we normally represent by beta. Please remember, if wave is propagating, we are representing with beta. So therefore this sign beta means whenever beta comes into picture, whenever z comes into picture, what does it mean? We are writing I in terms of the spatial system, in terms of the spatial coordinate system, not a time domain. We are simply writing them into a coordinate system, spatial coordinate system. That means the domain is going to be spatial domain, not the time domain. So whenever I introduce beta and z, the domain is now going to be the spatial domain, not the time domain for us. So therefore, by keeping in view, directly we are writing these two equations, which normally going to include direction of propagation with respect to the height of the antenna and propagation constant beta. So keeping in view these two things, we normally going to elaborate this particular thing. Now after this, what about the total vector potential that we can write now? See this part, this entire part, what I can treat, I can call this entire part as some A. Okay, so where I can say this A becomes equal to A1, A2 for our simplification purpose. So this actual total potential in a spherical coordinate system, in a system like half wave dipole, we can write as equal to, we will simply integrate all the way for, this is going to be minus h to plus h, height of the antenna is going to be minus h to plus h. So therefore we will take minus h to 0 and 0 to plus h, that means minus h to 0, z is equal to 0, and 0 to plus h. We are going to integrate further with respect to z coordinate. Therefore we integrate this component with z, we integrate the other component with z. What is this component? This is this component. So that means the differential component is going to be dz for us, z axis for us. Therefore we normally integrate with respect to z as per this particular total vector potential is concerned. So whenever we have to find out total vector potential, we simply integrate overall over the limits minus h to plus h. So we normally going to write it like this. Now what is our system of consideration now? We are considering the capital R. So here this R is nothing but going to be the diagonally, it is there basically, R is going to be there diagonally. Now here this R I can write as in terms of this R can be written as equal to R minus cos theta. See, as it is, this theta is known as elevation angle, phi is known as azimuth angle for us. So elevation means what? It is going to make an angle with respect to y axis. Phi means what? It is going to make an axis with respect to x axis. So keep in mind that this is what our system, say for example this is x, this is y, say this is z. Okay. So now our spherical coordinate system is like this. This is our spherical coordinate system. Right, here in the surface we normally going to take a point here. So that means here we normally going to erect a line from here. We erect a straight line here and we draw a straight line passing through this. So now this angle is nothing but equal to phi. Okay. Now here this angle is normally going to be equal to theta. Please keep in mind, we are representing in terms of the spherical coordinate system. So therefore this is theta. Theta is making angle with respect to y axis. Here with respect to y axis. But what I want is, I want this angle. So basically, if at all we want to get with respect to y, we will be getting a sin theta. Now I want to reverse. So therefore I will be getting cos theta. So therefore I am going to write this as r minus r cos theta component. So therefore the capital R becomes equal to simply r minus r cos theta. Now for simplification purpose, what we do, for a very long distance, this particular r cos theta becomes equal to 0 for us. R cos theta becomes equal to 0 for very long distance. Therefore this capital R is made approximated to small r, and we represent this capital R is equal to small r is actually represented for where? Represented for denominator. Okay, so in the numerator denominator we have r here, in the denominator we have r. So for this r we represent this r. Okay, now coming to numerator part, we normally not going to do this. So here in the numerator part, what is it I have now? E power minus j beta r I have in the numerator. So that remains as it is. So I can write A is equal to what now? This is nothing but A for me. Mu by 4 pi e to the power mu by 4 pi. Okay. So this I, what is the value of this I now? This I can write as equal to Im sin beta h minus z. So I am writing this Im sin beta h minus z by r into e power j beta r. This is what my A basically. Okay. So which part is changed now? So I am taking this r is equal to some r dash. Okay. So I can just remain that r, I don't change that r. Now in the numerator part I got an exponential component e power minus j beta r. So this I can expand it equal to what now? E power minus j beta r becomes equal to r minus r cos theta. So therefore this is nothing but equal to now e power minus j beta r minus into minus plus e to the power j beta r cos theta I can write. Okay. Now we are considering what now? We are considering a half wave dipole. As we are considering a half wave dipole, we can write L is equal to 2h, because I consider this as minus h, this is going to be plus h. And also one more equation that we have is L is equal to lambda by 2. Why is that I have written L is equal to lambda by 2? I have written L is equal to lambda by 2 because we are considering a half wave dipole. Now using these basic two equations, we will get the relationship between h and lambda. So please take down the first initial part for the derivation. Okay, this is an important derivation. Sometimes this question may come in the end exam. So please take down this derivation clearly. We are going to start from the, I just wanted to repeat once again. We are starting from the magnetostatics, and based on magnetostatics we can write B is equal to del cross A, and from Biot-Savart's law we can write dA is equal to the differential magnetic vector potential is equal to K times IdL by R. K times IdL by R I can write. Okay. Then after that, what we normally doing now, we are simply integrating on both sides to find the effective vector potential. Then after that, what we are doing, we are simply solving that equation, and we are replacing here I into dl. By keeping in view of a spherical coordinate system, we are converting this I into dl in terms of the volume integration, because in spherical coordinate system we consider the volume integration. So we are taking volume integration. After that we are simply solving that particular thing by considering the resistance, by considering the distance r. Okay. Then after that we are simply multiplying it with respect to e power minus j beta r. Why is that e power minus j beta r? Because the wave is normally going to get propagated, okay, in a direction specified, where it contains all the complex components. Since the wave is going to contain all the complex components, we are simply multiplying with e power minus j beta r by r. So that is the equation we are having. Then after that we are simply solving for that with respect to what is that volume integral j into d omega. Now if you consider the electric current is flowing through the dipole terminals, then what we can write, we simply convert volume integration to the line integration. So after we convert this volume to line integration, we simply substitute for integral of volume integral of j dot dv becomes equal to line integration. Okay, line integration j becomes equal to now IR into dl along the z direction. So after this, what we normally, so we were solving that equation now. And for dipole antenna we are considering it as a differential element, and we are extending that, where I is normally going to become taken as a constant parameter, because along z direction we wanted to find out the integration. So therefore the I is taken outside. Now here this I is normally going to be, if it is going to be asymptotically distributed, then we can represent I in terms of the sign component only. So when I go consider in terms of sign component, we consider in terms of sign component along with the propagation constant, okay, and the wave propagating along z direction, right. So similarly we normally extend it for h plus h minus z for z greater than 0, and sin beta of h plus z for z less than 0. And next we solve that equation for total vector potential. So for total vector potential, we once again further integrate the equation for the limits minus h to plus h. So while integrating that, what is that we have to compute now? Finally we should compute for the value for a1 or a2 or a. Okay, so to compute that particular thing, what is that we are doing now? We are considering the spherical coordinate system. In that we are that means we are assuming that the antenna is placed in the spherical coordinate system, and we have to find out the distance r. To find out distance r, how we found out? We found out simply is equal to r minus r cos theta. For a very long distance, r cos theta is taken as equal to 0, and therefore for the denominator part we approximate r is equal to r, but for the numerator part that r is normally going to remain as r minus r cos theta. Why? Because it is a changing component, because it is e power minus j beta r. The phase is normally going to change continuously while the wave is propagating in the medium. So therefore we are not substituting r is equal to small r in the numerator part. In the numerator part we have e power minus j beta capital R, so that we have substituted, and finally we have our destination is to go with the dipole antenna. So let us extend that dipole antenna condition now. So the basic equation that what we have got now, L is equal to 2H as per the dipole antenna construction. The next one is for half wave dipole, L is normally taken is equal to lambda by 2. So now here this L from here are equated. Therefore I will be getting the value for H. H becomes equal to simply lambda by 4. Now by letting lambda is equal to 2 pi, what we are going to have now? H becomes equal to 2 pi by 4. So therefore I can write H is equal to lambda by 2. So the H value is normally equal to pi by 2 that we have got. Now what we do now, this H value is substitute in the previous equation whatever we got, sin beta of H plus Z. So here H is, and now see both the parts, positive as well as negative parts, we normally going to have sin beta of H plus Z becomes equal to sin. So now finally we end up this class by doing this particular little thing now. So this is going to be sin beta of H minus Z. Now this H will represent with we replace with pi by 2. So it becomes simply going to be sin pi by 2 plus theta, sin pi by 2 minus theta, which is nothing but equal to cos theta. So therefore sin beta of H plus Z and sin beta of H minus Z can be written as equal to simply cos beta Z. Now we have to solve that particular equation. So in the next class we will try to extend this and we will try to solve this particular equation to get into the final solutions. Thank you very much for